Hi, everyone. Welcome to this series of applied sessions. My name is Louis Bertucci. I'm a researcher at Institut Louis Bachelier, and I've been working on blockchain for quite some time now. So now we will go through a series of 3 applied sessions. Okay, and the first one being about smart contracts. So what is a smart contract? So as you saw during the lectures, the Ethereum network actually runs a virtual machine, which is called the Ethereum virtual machine. And this virtual machine is run in a distributed fashion. Okay, so just like any other virtual machine, it's when a computer emulates kind of another computer, and you will see why that's important. So this kind of EVM computer runs in a distributed manner, meaning that it does not run in a single place, but instead it runs on a set of computer nodes. Okay, and each nodes are going to be called the Ethereum nodes, and they're going to have their own version of the Ethereum virtual machine. So just like it will roughly work as any other computer you may think of, except it will be in a kind of a virtual way, and you will see exactly what that means. So the way the EVM can maintain its state, okay, we will see what can be in the state. The state, if we compare that to your very own laptop or your own personal computer, would be kind of the memory. Okay, the memory on the hard drive, it will be what's on your computer. What does the computer know about the state of the world, essentially? So the way it works for the EVM is that it will start with an empty initial state. Okay, it would be like the first block or the very beginning. The state will be empty. Okay, and then as blocks are mined on this Ethereum blockchain, the state will change because block contains information to perform what's called state changes. Okay, state changes are actually transactions, and we will see some example of the state just in the very next slide. And there will be consensus that will form on every single block, and as long as all the nodes in the Ethereum network agree on the initial state, which is actually empty, and agree on the series of blocks, which are state changes. And by the way, state changes are always completely deterministic. There is no randomness. So as long as you agree on the whole state changes and the initial state, every single Ethereum nodes will have the exact same view of the global state, what's called the state, at any point in time. Okay, and this is why what allows the blockchain to exist and this distributed computer to run. Okay. Sorry. So this is a visualization of the blockchain and the state changes. So you see here there is the state, for instance, at time t, and then you have the state at time t+1, and so on. And you have a series of transactions that are actually this yellow triangle that contains everything any Ethereum nodes needs to change the state from state t to state t+1. Okay, so what can the global state contain? For instance, it can contain the balance of every. I mean, it does contain the balance of every single address. Okay, on the Ethereum network. So, for instance, the state at time t can be Alice as 10 units of Ether, for instance. And in the update from t to t+1, she sends 1 unit of Ether to Bob. So now at the state t+1, Alice has only 9 units, okay, and so on and so forth. So this is really how it works. And what's important is that the blockchain, which is shown at the bottom of this slide, does not actually contain the state. Okay, it contains the initial state, and then it contains the series of updates to change from one state to the next. Okay, and the state so it can be recomputed based on the blockchain, but it's not actually in the blockchain. And in that state, so you have the balance of every single address, okay? But you have also, for instance, the list of smart contracts that are actually programs. We'll talk more about that in a minute. Programs on the Ethereum virtual machine, and every program, every smart contract can also have its state. Okay, so just like a computer, a virtual machine, we'll see that you can install program on this computer, and the action of installing a program does actually change the state and will be contained in a transaction that will be contained in a block. Okay, these updates from T to T+1 are actually blocks, okay, on the Ethereum network. So what are smart contracts? As I said, just like any regular computer, you can install and run programs on the EVM, or the Ethereum virtual machine. So the way it works, it's a bit different than a regular computer. Essentially, the main difference is that once a program is installed on the Ethereum virtual machine, essentially anyone can use it. Okay, anyone can access it, can view its state. Okay, this is completely public information. This is made on purpose. Of course, in the logic of the program itself, or the smart contracts, developers can prevent people from making some actions. You can specify groups of users or things like this, for instance. But in principle, everything would be public and visible, okay? And so that's one part. And the other part is that anyone will be able to install a program on this distributed computer, okay? There is just one single instance of the Ethereum virtual machine that runs on many different nodes. But every time someone installs a smart contract on the blockchain, it's being installed for everyone, okay? And so everyone can see it, and everyone can use it, and so on. So in the diagram, just on the right end of the slide, you see that, for instance, Alice may install a smart contract A in a block, okay? So the fact of the action of installing a contract will change the state, so it will be contained in the block. And then at a later block, maybe Bob will use the same smart contract A, okay? And this is really at the very high level how it works, okay? We will see, of course, some details on what you can do with that kind of programs and smart contracts. But it's important to remember also that every single smart contract can maintain its state, its very dedicated state. And we will see that this will be, of course, very important to create useful applications, essentially, okay? So the last thing is that, yes, so you don't write just code for the virtual machine in a very simple way. I mean, the code that the EVM actually understand and process is called the bytecode. Okay, and the bytecode is the figure you see here. It's I don't know where it's from. It's an example, a random example of some bytecodes. Okay, of course, no one will ever want to write code like that, at least like a full program like this. You can write that kind of programs, very specific programs to run some optimizations and things like this. But no one will write a full program with this code. So the way it will work is that there will be a high level, what's called a high level programming language that you will write that will resemble like a programming language you might be used to work with. And this programming language will get compiled into this code. Okay, so this is called a translation or a compilation. And then this code will be sent to the blockchain and executed and so on. So there are several high-level programming language that you can use to write smart contract on Ethereum. The two main ones are Solidity and Viper. We will use Solidity here because it's the most widely adopted, even though Viper, for those of you who are interested, you can check out Viper. Viper is also popular for some applications. So the way it will work is that a developer, a team of developers willing to create a new application for the Ethereum blockchain will write the code in Solidity. Then they will compile the code into this EVM bytecode, okay? And then they will send the EVM bytecode to the blockchain, to actually a special address that will be the address 0, but you don't have to care too much about that. This is details, but essentially anyone will be able, by sending the bytecode to the blockchain, to kind of installing the smart contracts. And then the EVM, so the virtual machine, will receive this bytecode and instantiate the program, essentially, and give it an address, and wait for other users to come and to interact with that program. Okay. So again, anyone can call this smart contract, and this is really the power of the blockchain. So when the EVM receives a smart contract, it will assign it a unique address, and other users will be able to use this address to interact with that contract, and that contract become what's called callable. Okay, you will see just in a minute real smart contracts or real example of smart contract. So this will all become clearer. So don't hesitate to come back to this slide deck, of course, once you have seen the code. Okay, and you will see that smart contract is actually a series of functions. Okay, it's like an API. You have a list of things you can do to interact with the contract, and users, anyone, will be able to run a regular Ethereum transactions, calling the address of that programs, okay, and to specify exactly what functions of the API of that programs you want to call. And you can also send through some arguments or things like this. And also, this is also really powerful in the blockchain ecosystem. It's the interoperability. Okay, that's native essentially among smart contracts, which means that a smart contract can call another smart contract, and so on and so forth. Okay, so you will maybe see, we will not do that too much, but if you look into this, you will see that a lot of very powerful applications are being allowed essentially by this interoperability of smart contracts. The critical part of this is that smart contracts cannot self-execute. Okay, and this is really important to understand and remember. So a smart contract can call another smart contract, but it has to be triggered by a regular user account, if I may. Okay, the regular user accounts are called EOA, for externally owned accounts. And these regular user accounts will pay for the fees of the contract execution of the whole series of the contract execution. Okay, if a user called a contract that interact with 3 other contracts, these original users will pay for the all fees. Okay, because also this is really important, and you have seen that in the lessons. When you want to use the blockchain, whether it's for regular transactions or using smart contracts or anything like this, you have to pay fees. Okay, because you're making miners and validators work to validate the state change you're willing to perform on the blockchain. And for that and for other reasons, you have to pay fees. Okay, and when you are using and especially developing smart contracts, you have some safeguard that you can use, but you have to be careful, because if you call a contract, so you're trying to use a program, whether it's your program or the program from someone else, and the execution of that program fails at some point, okay, because I don't know, you're trying to divide by 0, or you're trying to read from an address that does not exist, or something like this, like very technical bug, or also more economic bug failure. If you want to, I don't know, if you have only 10 units of a given token and you're trying to send 12 units, that will of course fail. If it fails, all the pending state change that have been performed until that failure will be reverted, but the original user will still pay the fees. Okay, the rationale is that validators and Ethereum nodes must have run this program until it fails to see that it will fail. Okay, so you still have to compensate them for that work in a sense. Okay, so this is really important, and this is why you want to be extremely careful. So for the vast majority of well-known programs and smart contracts, especially for DeFi protocols and things like this, it's very unlikely that there will be a random failure like that. But when you're using less known smart contracts, or when you're developing your own smart contract or things like this, you have to be careful with that. We'll see that the tools you will use, most of them will try to warn you that a transaction may fail, but it's not the same as running the transaction on the nodes and actually seeing that it failed. Okay, so this is important. So if we look a bit deeper into, from the technical perspective, right, what's actually in the smart contract? It's all this I have said, but it's just a better view of that. Okay, so you see that in the smart contract, you may have more, but those are the 3 main elements. You have an internal state. Okay, you have a public API and you have a protected API. So the internal state is all the data that you may want to store on the smart contract. So for instance, it could be the address of the owner of the smart contract. So whoever installed these smart contracts could be remembered to in the internal state. In the internal state, you may also have the address of a token that you will use for some applications or things like this. This is just data, of course, and this is data that can be changed. This is essentially the purpose of getting a smart contract and modifying its state. And how would you modify the state of this smart contract? Through the API. So you will have a public API and a protected API. You see in the public API, here is just, of course, an example. It does not really mean anything, but we will see some real smart contracts later on. The public API, you have a function to get the token address. Okay, so that can be used to retrieve the internal state, to retrieve data from the internal state through the get token address. And then you can also have a function set new token address. Okay, so if you call the function set new token address with a new token address, it will essentially modify the internal state and replace the token address by the new one. Okay, again, don't try to figure out what can be useful. This is just an example. You may have more. And then you have also some protected API. So the protected API is a list of functions that only specific users can call. Okay, and for instance, in that very simple smart contracts, you can have a function to change the owner of this particular smart contract. So this is actually quite useful in real smart contracts, I mean, because there are several instances, several times when you want to transfer the ownership of a smart contract to an entity, to a new user, to some kind of advance. You can even transfer the ownership of the smart contract to another smart contract, for instance, or things like this. It can get quite complex. But what's important is that, of course, not anyone will be able to call this function change owner. Otherwise, anyone can claim ownership of that contract, and this is not what you want to do. So this function is protected because at the beginning of the execution of this function, there will be a very simple if condition, if statement that will check if the address of whoever is trying to trigger this function is, for instance, the current owner. Okay, if we want to make only the current owner able to transfer ownership to someone else, the change owner function will only be able to be called from the owner account here. Okay, and if the address of whoever is trying to change to call that function and to trigger a change of ownership is different from that one, the function will fail. Okay, so this is a very simple example, but we will very soon see some real example of smart contracts. So Solidity, as I said earlier, Solidity is by far the most popular high-level programming language for writing smart contracts. It was designed very early on, I think at the same time the Ethereum blockchain came out by Gavin Wood, who was actually one of the Ethereum co-founder. So it has a structure similar to JavaScript, but it is statically typed and supports inheritance. If you don't know what that means, this sentence, it's really completely fine. You don't have to be a developer to follow this class and to follow this session. You don't have to become a developer. Okay, it's really fine. You will see the code we will use are really kind of easy, and most importantly, you will not be asked to directly write some code. Okay, the smart contracts have already been written, so you will just play around with them, try to compile them, try to use them to deploy them. Okay, of course, if you want to go the step forward and try to understand what the contract does actually in details, you're free to do it, but this is not the point of this session. Okay, so in this first session, I will just in a minute show you an example of a smart contract, and in session 3, okay, in the applied session 3, we will actually use a wallet and use an environment to play around with smart contracts. Okay, so you will be able to really experiment with that, and this is something you really should do, even if you're not, if you don't have a tech background or something like this, because this is really the power of the blockchain. Okay, you can do it, and so yeah, this is really interesting, and it will really improve your understanding of our blockchain, what a blockchain is and what a smart contract is. So as I said, let's switch to this. So you will have the link to this GitHub repo. Okay, it's a GitHub repo that I've created. Okay, so you will, if you hit the link, you will end up here. Okay, so you will see there is a folder for session 1, a folder for session 2. We'll of course come back for session 2 later on, but for now, let's open the folder for session 1. And here you will see 2 files. Okay, there is the simple faucet and there is also the augmented faucet. So the simple faucet, let's open it. And here you see a smart contract. Okay, so here this is an actual running, I mean, a real smart contract that can run. Okay, you'll see that it's a kind of a stupid one. Okay, but it does work. Let me maybe, yeah, okay. I just zoomed in a little bit. So let's go through a bit of this smart contract and let's hear what it does. Okay. So here you have at the top, very top of this of the code, you have some technical statements. Okay, essentially this one tells what version of Solidity should be used to compile the smart contract. Okay, but this is kind of technical. You don't have to worry about that. And then you have here a declaration of one smart contract. You declare a new contract with the keyword contract. And this is the name of the smart contract. So in this example, the smart contract is called the simple faucet. And you see, if you look carefully, so every line that starts with a double slash like that are actually comments. So they are completely ignored by the compiler. They are just made for you to understand what the functions are doing, and also for me to remember what I wanted to do, like for the developers to remember what I wanted to do. Essentially, you can, those are not statements that will be sent through on the virtual machine, on the EVM. So what is the actual code? Okay, you see that there is one function here and one function here. Okay, so let's start with this last function. This is a very particular function. Okay, this is a function that essentially has no name. Okay, that does not do anything. Okay. It's a very, very particular function, but why is it useful? Because it essentially tells the smart contract to accept any incoming amount of Ether. Okay, remember that Ether is the cryptocurrency on the Ethereum network. And if you're trying to send Ether to the smart contract, it will accept it because there is this function which is external and payable. Okay, even if it does not do anything. You could have, for instance, perform some checks. You don't want to accept incoming payment from that person or do something like this, but here is just open for anyone. Okay, if you don't have that, the smart contract will reject any incoming amount of Ether. So here you don't have any particular state, okay, because it's very simple. The only state is the balance of the smart contract. Which is not actually stored inside the smart contract, it's just maintained in other part of the EVM state. The function that's most relevant here is the function withdraw. Okay, so you see that to declare a function, you have the keyword function, then you have the name of the function, and then here you have the argument. Okay, so the function withdraw accept an argument amount and the, sorry, okay, sorry, let's look at that here. And the uint that you see here is actually the type of the argument amount, and uint is an integer type. Okay, so the function withdraw accept a number as argument. Okay, this function is public, meaning that it's part of the public API. Anyone can call it. It could have been private, for instance, but this one is public. Then there are two required statements. Okay, the first required statement is that the amount that is being tried to be withdrawn, okay, is lower than 0.2 Ether. Okay, so required statements, I mean the required function is a native function of Solidity. It simply assesses and tells if the condition in the first argument, so before the comma, if this condition is true, it continues execution. And if this condition is evaluated as false, it will stop execution. Okay, it will return an error and it will return this as the error message. Okay, so essentially this required statement here simply ensure that the amount you're trying to withdraw is lower than 0.2 Ether. And then the second required statement here will also, it's very technical and simple one. It will simply assess that the amount, again, you're trying to withdraw is lower or equal to the balance, the Ether balance of this contract. Okay, and how do you know the Ether balance of this simple faucet contract? You have this very technical statement, okay, our way to write Solidity code. Oops. You have the this keyword is actually refer to this, the current instance of the simple faucet contract, and this dot balance is simply the ether balance of this contract. So if the ether balance is larger than the amount trying to withdraw, you can continue execution. And so this is the real statement, okay, what actually the function is doing. It will send, so it will transfer the amount to the message sender, okay? And who is the message sender? The message sender is whoever trigger the execution of this withdraw function, okay? And you want to send some ether to this message sender, so you have to wrap it into this payable function, and then you hit the dot transfer. You transfer how much? You transfer amount to the message sender. Okay, so if you carefully followed the explanation, you will understand that a faucet contract is a very simple contract in which anyone can send some ether to, okay, and also anyone can withdraw ether from this contract, okay. Of course, with these two conditions, meaning that you can only withdraw 0.2 ether at a time at most, okay. So this is really probably the most simple version of a smart contract you can see, but it already tells you how states are managed, okay. Here, a smart contract can hold some ether, okay, so you can send smart contract to the ether. Once you have sent smart contract to this, once you have sent ether to this smart contract, the only way there is to withdraw it, okay, is by using this withdraw function. If, for instance, you forget to write this withdraw function, so you have only this, you deploy the smart contract, you send ether to that smart contract, the ether you sent to that smart contract will be locked in the smart contract forever. There is no way of decreasing the balance of a smart contract other than using its own API and its own function, okay? So this is also why you want to really be careful. But again, this is a very simple example of what you can do with a smart contract. We will not cover it in detail here, but if you head to the augmented faucet, you will see that it's a slightly more complex smart contract. You will have in the repo also explanations, and you have comments essentially everywhere. So you will see that this one is a slightly more complex faucet, more complex in the sense that it will only allow for a given number of users to withdraw. Okay, so anyone can send ether to this contract, but there will be a maximum of, for instance, 3 different accounts, 3 different users that will be able to withdraw from this augmented faucet. Okay, so this is kind of the improvement you can make. So I will leave you go through this contract, and remember that you will have a live session at some point. So of course I will be here to answer any questions you might have on this augmented faucet. Okay, and that's it for this first supply session. See you for the next video.